Go. Hello and welcome back to Calculus1. We are starting chapter 5, chapter on integration. We did learn basics of antiderivative and integration, but we're going to learn much more in this chapter, including some limited application to integrals. We start the chapter with the section that approximates area under the curve. So I can draw constant, this is purple. I can draw constant function y equals 4. And then let's say I'm interested in area between 2 and 9.
What are we looking for here?
Area. So if my function is y equals to 4 and I'm looking for the area from 2 to 9, well, that's going to be the area of this rectangle. We know that the area of the rectangle is, as you told me, length times width, x times y, whatever you want to call it. Length times height, fine. Area in this case is, what's the length in this case? 7. Times the height is 4. So the entire area is 28 units squared. Centimeters squared, millimeters squared, inches squared, miles squared, whatever you are talking about. Okay, that's great. Area under the curve for this triangle that passes through 1, 2, 3, again 4, 1, 2, 3, 4, 5, 6, 7. Great. What's area for the triangle? Yes. 1/2 base times height. So 1/2 base is 7, height is 4, so 14 units squared. Good. So that's all cool. Now what happens if the function curves? So if it's not a straight line, for me to have a triangle or a rectangle or a square or even a trapezoid, which we can calculate, right? What happens if you have some function that might look like something like negative x squared, and just take half of it, let's say? So what's area here? Now this is where the method that I want to teach now kicks in. So what I can do in this case is I can partition this area with these vertical divisions so that they all have the same. It's not necessary to have the same, but it's much easier if they have the same division on the bottom. And you can partition in whatever amount of these stripes that you want. So in this case, let's say 3 is good enough. So if this is 0 to 6, then these partitions are at 2 and 4. Now, I need you really to pay attention, and you can write it later. What I'm going to do now is I'm going to go to each one of these stripes and use the left hand point that is touching the function to create a rectangle. Left hand point for the rectangle number 1 is right here, and I draw the rectangle. Then for number 2, left hand point is touching the function here, and I draw the rectangle. So I am completing rectangles because I didn't have rectangles. Well, now I have 3 red rectangles which I can easily compute the area of. Now it's important to see that I use the red points and call those x0, x1, and x2. So x0 is equal to 0, x1 is equal to 2, and x2 is equal to 4. So those are the x values, and those x values will produce the y values. Y value 0 will be function computed at x0, which is function of calculated at 0. Y1 is function computed at x1, which is f of 2. And finally, y2 is function of f of x 2, which is f of 4.
And you said this is for negative x squared? Right?
Well, no, it's just negative x squared with something, 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 because negative x squared would be at the origin going down. This is negative x squared plus whatever I need to have, so it goes to 6 over here.
Right.
We can find the formula, but no. When I have a curved line, I can't compute rectangles because I don't have a rectangle, right? I have a curve. So what I can do is I partition into these vertical stripes. Now you pick how many you want. The more you have, more calculations you have. The less you have, less calculations, but more error, and we'll see that. So it's a trade-off. There's never a free lunch. So what's happening here is I use the left-hand point. You see that in a first rectangle, there are 2 corners. There are 2 corners that I can use to draw the rectangle. I can draw the red rectangle that is going to be above the function, or I can draw the blue rectangle. Now that will be for the right points. The blue rectangle would be this one, going down, because it's emerging from the right point. But look at the blue rectangles. You see that the last blue rectangle is actually 0? We are losing entire area in a third space. Do we see that? So for this particular picture, the right ones are not that good, right? But then the left one is also not so hot, because look at the third one. All of the, yeah, it overestimates. Look at this. All of this is error. Plus all of this is error. Plus all of this is error. So you have all this error that adds up. Yes?
Can you like switch between right and left for each partition?
It's just headache. I'll explain it.
So wait, all right.
So now, give me a second. So the exact area is approximated by the area which we get when we add the 3 areas that we approximated. We know it's wrong, but it's the best we can do without software. So this area is x1, y1 plus x2, y2 plus x3, y3, and you have your x1s and x2s and so on up there. Oh, I used 0. Now I gotta 0, 1, and 2. x0, y0, x1, y1, x2, y2. Fixed all of that. I have 3 rectangles, 3 areas, 3 terms in calculation, and we are going to get some kind of a number. Question is, can I do better? And the answer is yes. Make a smaller partition. I can go at 1 and 2 and 3 and 4 and 5 and 6, right? That's going to give me double the amount of rectangles to calculate, but there will be less error. And the question is, how much error you can live with, right? That depends on your application, right? Because we all know when they're building houses and things, like go ahead and try to find a right angle anywhere, right? It's like, it looks good, just, put it down. Try to use the same precision if you're making a piston for a car, right? It's not gonna fly. If there's just a little bit of room next to it for gases to escape, you're not gonna get any power from that engine. So the precision and the tolerance there, the error, has to be minimal. Try to think about nanometer technology to create processors, right? They're talking about 7 nanometer technology. 7 nanometer technology. Guys, it's just few atoms thick. Few atoms thick. Atom is 10 to the negative 15. 10 to the negative 15, right? I am of the order 10 to the 2. Of order 100. So 17 orders of magnitude smaller, right? So in certain cases, you need huge precision for certain industries, right? For research, so on. You want to do particle physics? Yes, right? If you are building a road, you don't have to have a precision of 17 decimals. That's given. So your application will drive how many of these rectangles you want to have, because the amount of rectangles will govern the precision of your calculation. Now, if any one of you want to call yourself a computer scientist and a programmer, your job is to, in whatever programming language you like, to code this tonight, right? What do you code? You simply code, ask for the input for the function, ask for the interval where the function is on, ask for number of rectangles, and the computer should be computing the rest in a formula, right? That should not be that complicated. 30 minutes. Done. Why? Because your computer and your code should be computing this at 10,000 rectangles. While you sweat to calculate 4, right? And it takes you 5 minutes, computer should have 10,000 computed in a second, right? Telling you the efficiency, which is why you're not getting hired to do this by hand. You're hired to model things and understand what application calls for which precision, so you can program the computer to give you exact values you need. That's your job today. It used to be you needed to know, right, to compute, and then you get the legion of graduate students to sit there and calculate 10,000 values, right, one by one. Good old times, no calculators, no computers. Today, just write a few lines of code, right? I had a student in my my last Calc 2 last semester who coded pretty much everything we talked about in class, coded on the spot. And he made 10,000 for Calculus 2 made a 10,000 approximation, 10,000 term approximation to a function, something in Calc 2, you guys will see that, and then went home and made a billion approximation when Ryan had more time. That's how you further your skills, right? Because that's the real work. You're not gonna sit here and grind this by hand. Now, obviously, you will on the exam, but for application. So let's do a full problem. Let's say you want to calculate area under square root of x plus 2 on 3 to 7. Nah, I don't want 3 to 7. Let's do 3 to 7 with 4 rectangles using right points approximation. Right point approximation. Now, we know what the graph of square root of x looks like. We need to shift it 2 units left. Very good. So we're going to draw the square root graph. Go at -2. Whee! There we go. Then we're going to go to 3. And 7. And shade lightly the area in question. So now we're going to use, so to get the 4 rectangles, we cut the area in half and then each one of these in half. And now we have 4 regions like that. And because they asked for the right point, in each one of these you would use the right point to draw the rectangle, which means it's going to go above. So we know that the area that we calculate is going to be bigger or smaller than the actual area? Bigger, right? Because these rectangles went above the function. So what do I have? The area will be approximated by how much is each one of these widths? 1. Now there is a cute formula which we will use a lot later and tomorrow. Delta x equals b minus a over n. Delta x is each one of these widths over here on the bottom. So we see that the delta x is equal to 1. So what's the first rectangle? First rectangle is square root of 4 plus 2 times 1. Or you can say 1 times square root, whatever. Plus square root of 4 plus 3. No, square root of 5 plus 2. Square root of 5 plus 2 times 1 plus square root of 6 plus 2 times 1 plus square root of 7 plus 2 times 1. So these are our calculations. Each one of these, this is your f of 4, this is your f of 5, this is your f of 6, this is your f of 7, times delta x each. Because the area of the rectangle is length times the width, or height times the width, or x times y, whatever. So we were calculating the function at each one of these points so we can get the height, and we know the width is delta x. So now we compute this. So area is approximated by square root of 6 plus square root of 7 plus square root of 8 plus square root of 9. And then we plug all of this into the abacus and get the answer.
All right.
6
Well, we
plus.
know what square root of 9 is. That can be simplified.
I will use the value. Yeah, I'm sorry, but that's it. You are dividing these into these stripes, right? Each one is a rectangle. You will compute the values for y's at the points of interest, either it's a left or it's a right, and you will do that for each individually, and then you just add the values at the end. I just want to go and calculate not the exact, but much better value, and see what it is. Yeah. So I don't want to call this exact value because it's not exact value. 10.5. So area under the curve, when we learn to compute the exact way next class, for this particular problem, an answer should come out to be 10.5. We got 10.9. That's 40 cents off. That's not that bad. It's good. We approximate. Can we make this better?
Yeah. Yes.
How?
More rectangles.
More rectangles. Now, if you want to go and cut each one of these in half, you will have 4, 4.5, 5, 5.5, 6, 6.5, and finally 7. You will double the amount of calculations, but you will reduce the error. The content of the next lecture is that if you create infinitely many, infinitely thin rectangles that fit under the curve, you will get exact area. That's the topic of the next lecture for tomorrow. Today, we are playing in sand over here with the little plastic shovels, right? Heavy stuff is tomorrow. Let's take a look at another one of these. And then we will take a look at what we call summation notation, which we need to learn so we can survive the next class. Let's take
Is pi going out on a limb, but would it be more accurate in the rectangles if you took like a tangent line at a certain point? And then
It's called trapezoid rule, and it's Calc 2.
okay.
I love your brain. So you are going to see those, and then there will also be arcs like this called Simpson's rule, which is a quadratic approximation. Then one you're not going to see until you hit graduate school, cubic splines. So you can take graduate numerical analysis. There is a lot of stuff. but then, as I said, 100% of what you said is correct. Here is problem 19 from the textbook. Instead of using x and f and y, they are using t and v, and I picked it for a reason. So v as a function of t is equal to 1 over 2t plus 1. That's your function. It's a velocity function, right? So we have some physics, so everyone is happy. This is velocity in meters per second. They gave us that the interval for time, for problem 19, interval for time is from 0 to 8. And they want four rectangles.
With a vision.
Yes.
Are they going to tell us what side they want us to come from? Or?
Ha. They are going to ask for both left and right. So it's like two problems in one. Because the area that you're looking for is going to be squeezed in between those two numbers. One number is going to overshoot, other number is going to undershoot, which means that the value you're looking for will be between those two numbers. That's it. Now, you don't have to graph the function, even though it's easy. You don't have to graph the function. It is enough just to draw the x-axis so you can see the partition. So you can, well, x-axis, t-axis, the time axis, right? So you draw the t-axis, and you need numbers from 0 to 8, but you actually need only every other one because they want 4 rectangles, so 0, 2, 4, 6, and 8. 0, 2, 4, 6, and 8. I'm going to put red dots on the left approximations because you will have 4 rectangles that will be using red dots, and then you will have blue dots for the right approximations. So you will use the red values to compute. What's your delta x, by the way, for both calculations? Delta x is 2. Go. Function computed at 0 times 2 plus function computed at 2 times 2.
Oh, yes.
Cool. That was cool. That's cool.
No. I made a mistake. This is supposed to be 13. I gotta calculate everything from scratch. Well, it looks like we'll have to go with let's just go with 3 decimals and then we'll cut down.
It's close. Is that what you got?
I changed the value. So we can go with the 1 decimal here. Area for left rectangle points and area for right points. So now that means that the area you looking for is in between 0.9 and 2.8. Since we were talking about velocity in this problem, what you're calculating is displacement. How far you went. That's what you calculated. That's a terrible range from 0.9 to 2.8. That's terrible.
Yeah.
Right? It's terrible. But we know we can make it better. We just need to be less lazy, right? Instead of 4 rectangles, use 6, use 8. Or write a code, use 10,000. Right? To end this lecture, we need to talk about summation notation. It is the Greek letter, uppercase. It stands for sum, and it's a notation that makes our life easier when we have to add multiple things that are in order. So this is where notation kicks in. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus... Okay, I'm done. 1 through 8. Add them all. Well, that was annoying to write. Imagine if I had to write all the way up to 112. Plus 9, plus 10, plus 11, plus 12, plus 13, right? Very good, right? So you gave up at 36, right? Notation works this way. Method that this symbol stands for sum. So sum all values, say I, where I goes from 1 to 8. So it's, for those of you who are programmers, this is a loop. All right? If you know programming, this is a loop. Plug in the values 1 through 8 for I, one at a time. So this is where you start. This is where you end. So you have a start and you have an end. So your first value, I, is equal to 1, and that is this number here. Then you put plus because it's a summation.
I assume I stands for initial, right?
No, I stands for a value of a counter. You see that I equals 1 in the counter of the summation. And it just scrolls through all of the numbers and it stops when it reaches the value at the top. Yes.
Does the I to the right represent that it's going by an interval of 1 each time?
No.
So how do you know like what the interval is?
This is always scrolling through integers because it's a counter and it's an integer based counter, because we counting numbers are only 1, 2, 3, 4. You don't count 1.1, 1.3, right? You just count. If I'm to count people here, 1, 2, 3, 4, 5, 6. If I want to count desks, 1, 2, 3, 4. If I want to count clocks, 1, right?
Yeah.
So there are no decimals, no fractions. It is always, the counter I is always, always, always whole numbers, counting numbers. We could start at 0, but generally we start counting at 1. Half of your Calc 2 is that. So now, we have a lot of flexibility with this notation. We don't have to just put I there. We can actually write a function which contains I. Let's say I want to add I 1 through 4 of I squared minus 1. Now this is a formula. The first time around, for the first term, I is 1, so 1 squared minus 1, plus second time around I is 2, 2 squared minus 1. Next time around I is 3, 3 squared minus 1. Next time around I is 4, 4 squared minus 1, and then I have to stop because the last value that I can take is 4. I got the 4 terms from 1 through 4, and you can see that the value of I is the one that went 1, 2, 3, 4, right? So now you compute each one of these. You have your values. The first one is 0, plus 3, plus 8, plus 15, for the total of 26.
Yeah.
Are we agreeing on this?
Well, just about.
Let's take a look at another case. So I'm gonna separate these cases here. Yeah. Remember how polynomial had the formula of p of x is equal to a0 plus a1x plus a2x squared plus a3x cubed plus dot 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 plus an x to the n. This is the definition for a polynomial. You want the constant, that's just this puppy here. You want the linear line, well, here is your y equal mx plus b, right? Linear, mx plus b is there, good. Here's your quadratic, ax squared plus bx plus c. So all of the polynomials fit in this definition. Now summation notation allows us to compress this. Instead of having this huge string, we can just say, well, p of x is equal to summation. I starts at 0 this time because that's the first, a0 is the first, all the way to n, and then we have ai x to the I. These are the fundamentals of computer science programming and stuff, if you want to do loops and some cool stuff. So if you look at this, right, the first time around I is equal to 0. You get a0 x to the 0. How much is x to the 0? 1. So a0 times 1 is a0. Summation, so plus. The next time around I is 1. a1 x to the 1. a1 x to the 1. Plus. Next time around a is 2. I is 2. So a2 x squared. a2 x squared. And you just go all the way to the last term, which we call leading term, which is the one with the highest exponent, that gives us the order of the polynomial, an x to the n. So that's the way to describe the polynomial definition using summation notation. When you have summation notation, you can add them, subtract them, and kick the constants outside. The same way you can do integrals, derivatives, and limits. So one of the properties is that if I have a summation notation of a plus minus b, these are functions, then I can have summation of a plus minus summation of b separately. And if I have a summation of some kind of constant times, let's say f of I, you can kick the constant outside. So these are the standard properties you've seen for limits, right? And these are really, really cool. Because these properties now allow us to write our formulas for left and right sums for approximation of the area under the curve using summation notation rather than writing all of those terms and putting in 3 dots in. So our old notation was that area to the area of the left was f of x0 times delta x plus f of x1 times delta x plus f of x2 times delta x plus dot dot dot. Summation notation picks up that there is a pattern 0, 1, 2, and that's going to be in I. So now with this advanced notation, we can write that the area of the left points is going to be summation of x, f of xi times delta x, and I starts at 0 and ends with whatever n number of rectangles you have. And by the second rule up there on the top, we know that delta x is some kind of constant, and you can kick that outside, which gives us the compact formula. Area of the left points is delta x times summation I goes from 0 to n of f of xi. And this is the compact version of the formula we have seen before. Like we saw the formula in this light. There was, everything was expanded. Now we compress this. Also AR is going to be delta x, and that one starts with I equals to 1 to n of f of x I. Remember, because you're right, you have to, for the right points you shift by 1, right? This is not DD, this is old, and this is new. And it's just a notation, it's not concept, it's just a new notation, so we don't have to write all of those terms, just write the sum and say this is the formula that takes all of these values.
You recommend the compact formulas, right?
If you are going to Calc 2, and you are, it's going to be summation for 2 chapters, which is half of your Calc 2. So we need to know this notation. There are also 4 formulas that are going to be eventually used. We'll deal with that when we get there, which is tomorrow. So for areas under the curve in terms of approximations, guys, your job is to partition the area you have into these vertical strips. The number of vertical strips is actually the number of rectangles you have. then be careful whether you need left or right points. Compute the function values at those points, and then compute your delta x using this really cool formula, which we will see again tomorrow. This formula will be very important. And you just do just a middle school calculation, right? Length times width, and that will be it. So please try not to make this complicated, all right? No need. And then practice a little bit this summation notation, because tomorrow is when we actually get to use it for some more serious calculation than just shortening the notation. Yeah. Bye.